video, I'll be showing you how to use triple integrals in rectangular coordinates to calculate the volume or the mass if given the density function. Because we are using triple integrals, we are taking into consideration of three variables, x, y, and the new one is z. Basically, instead of using rectangular coordinates in a plane with x and y, we will be using rectangular coordinates in space, where the z-axis is perpendicular to both the x and y axis. So a volume of a solid Q is a definite triple integral of 1 dV. We can conclude that the mass of the solid Q with its corresponding density function equals to the triple integral of the density function, which is delta of x and y and z times dV. Similar to the way we created rectangular prisms to find the volumes of a region, we can use a triple integral to find the volume under a surface d equals delta of x and y and z with a new variable, which is z, included over a region by calculating the volumes of an infinite amount of cubes in the 3D solid. Let the change in the volume of one of these cubes in the surface equal the change in x multiplied by the change in y multiplied by the change in z. As we learned with Riemann sums, if we take the limit of the sum of an infinite amount of rectangular prisms, we actually get the volume under a surface z equals f of x and y. Similarly, if we take the limit of the sum of an infinite amount of cubes, we actually get the volume of the region D, or the mass of the solid, with the density function delta of x and y and z. Because we're in 3D, we can add an extension to Fubini's theorem from R2. Remember that Fubini's theorem in 2D states that there's no particular order of integration to express a double integral in terms of x and y. So dx can go first or dy can go first. Similarly, Fubini's theorem in 3D expresses a triple integral in terms of the iterated integral in x, y, and z with 6 possible orders of integration, shown here in the video with dx, dy, and dz. Let's consider that we integrate in this order: dz, dy, and then dx. Our inner integral will be with the variable z, obviously, dz, and the integral will be from g of x and y to h of x and y, where h is greater than g. And in the middle, we'll integrate with respect to y, from y equals g of x to y equals h of x, where h of x is greater than g of x. And in our outer integral with respect to x, we'll be integrating from a to b. Integrating with this fashion, we'll actually get the volume with the triple integral of f of x and y and z dv, or if given the density function, the mass of the solid. The hardest part of calculating the volume or mass given the density function with triple integrals is to define your bounds. Make sure to draw 2 pictures of the equations you are given with the question. One in 3D to find the z bounds, typically, and after using a 2D picture, which can be found by drawing the projection of the solid on the xy plane. Use what you learned to do when finding the double integrals to find the 2 other bounds, and in this example, x and y. Remember that the bounds of integration should never have the variable it is integrating with respect to. I hope my video was helpful in your understanding of how to use triple integrals in rectangular coordinates to find the volume or mass if given the density function. Thanks for watching.